Henry's law. At a given temperature, the partial pressure of gas in vapor phase above the surface of liquid is directly proportional to the mole fraction of gas in liquid. According to this statement, P is directly proportional to X, and remove the proportionality by using one constant, that is KH. That's why P is equals to KH into X. Here X is mole fraction of the gas. We know the definition of mole fraction of X. It is the ratio of number of moles of any one component to the total number of moles of the solution. So here partial vapor pressure above the liquid surface is equals to the KH into N2 by N1 plus N2. Okay, students. Now here P is partial pressure of gas, and KH is Henry's law constant. X is mole fraction of gas in solution. Okay. While doing some objective problems, instead of giving partial pressure of that particular gas here, partial pressure of the particular gas, they'll give here the total pressure and its mole fraction. By using this, according to Dalton's law of partial pressure, total pressure of the non-reacting gaseous mixtures must be equal to the sum of the individual gases partial pressure. So again, partial pressure of each component is equals to the product of total pressure of that gas mixture and its mole fraction. So by using this relation, we can easily to calculate this partial vapor pressure. Now, a graph is plotted between vapor pressure. Here the vapor pressure of that particular gas in a liquid above the surface and its mole fraction along x-axis and vapor pressure along y-axis. Now your example is mole fraction of HCl gas in its solution in cyclohexane. Example, one best example it is. Now a graph is plotted between the vapor pressure and its mole fraction. On increasing its mole fraction, nothing but solubility of the gas increases. Simultaneously, its vapor pressure also increases. Now, it gives one straight line, passes through the origin. That a straight line, slope of that line is equals to the KH value. Here, KH is Henry's law constant. So, based on that, maybe in object examination, they'll ask like, the slope of the line, a graph is plotted between vapor pressure and mole fraction of that particular gas dissolved in a liquid. If they'll ask, its mole fraction is KH. Okay, students. Now here the slope of the line is the Henry's law constant KH. Now that a KH is the function of the nature of gas. It is very, very important for objective and NEET and other competitive examinations. Now the same thing, if a graph is plotted between X mole fraction versus and its vapor pressure, it is very, very important graph. It also on increasing vapor pressure means its solubility and its mole fraction increases. Also it gives a straight line which is passes through the origin. It gives a one linear line, one straight line. Then for this graph, slope is the reciprocal of Henry's law constant. So this is a very, very important concept, students. Okay. Now, based on this Henry's law, there are some important points which are very, very important for objective theoretical concepts. For see here, the value of KH is different for different gases at the same temperature. Maybe in objective they will create one option as KH value is different for different gases at the same temperature. They won't give any different gases, same value they will give. So based on that, we will create one theoretical question in objective examination. Again, see here, students, easily liquefiable gases have less KH value, more soluble. More soluble indicates its mole fraction is more. Now, third one is for the same gas, as the temperature increases, the value of KH increases and its solubility decreases. So here students, a simple formula we know. So here the KH is equals to P by X. As the value of KH increases on increasing temperature, the solubility decreases means its mole fraction also decreases. This is very, very important for objective theoretical concepts. Here there are some important limitations about Henry's law. See here, important limitations. This is applicable at a low and moderate pressure, not at a very high pressure. If it is very high pressure, they are not dissolved in that. That statement is not true for this application. It is not applicable for more solubility of gases. It is not applicable at a very low temperature. If it is very low temperature, gases are easy to freeze out, cannot dissolve in the liquid. Okay, students. Now, it is not applicable for a gas which undergoes dissociation or association. If it dissociate or associate, what happens? They easily react and cannot exert any vapor pressure. This law is not applicable, and which cannot react with the solvent. These are some important limitations of Henry's law. Now, some important applications of Henry's law. Say it, students, to increase the solubility of gas in soft drinks and soda water, the bottle is sealed under high pressure. Say secondly, when scuba divers are moving deep in the sea, the solubility of atmospheric gases increase in human blood. When divers come up, there is a release of dissolved gas, and it leads to the formation of bubbles of nitrogen in our blood capillaries, which blocks capillaries. Hence, there is a medical condition known as bends, which is very painful and dangerous to life. To avoid bends as well as toxic effects of high concentrations of nitrogen in the blood, the tanks are used by scuba divers are filled with air diluted with helium, that is 11.7%, 56.2% of nitrogen, and 32.1% of oxygen. Say the next one. At high altitude, the partial pressure of oxygen is less than that at a ground level. This leads to low concentration of oxygen in the blood and tissues of people living at a high altitude and climbers. Hence, low concentration of oxygen in blood causes to become a weak and unable to think clearly. Symptoms of a condition is known as anaxia. Okay, students. For this, I'll give a simple explanation. See here. See it, students. First one is to increase the solubility of carbon dioxide gas in soft drinks and soda water. The bottle is sealed under pressure, high pressure. See here. See here, students, this diagram, this simple explanation. Generally, in ground level, temperature is 25 to 27 degrees Celsius, and pressure is 1 atmospheric pressure, that is in ground level. So, to fill the carbon dioxide in this water solvent, certain pressure required. Without this pressure, this carbon dioxide gas cannot dissolve in water. That's why, while filling the carbon dioxide, the bottle is sealed with carbon dioxide at high pressure, and also some here air gaps required because it exerted certain pressure. The exerted pressure entered into this air gap here. Okay, students, this is for first application. So the next one is scuba divers are moving with the deep sea, the solubility of atmospheric gases increase in human blood. See here, I'll show a simple example here, students. From ground level, here ground level temperature is 25 degrees Celsius and pressure is 1 atmospheric pressure. Whenever the people are moves towards depth areas like sea areas, scuba divers here, the pressure at a ground level is less than deep sea areas. That's why the gas present in atmospheric air, that is nitrogen gas, easily react with oxygen. And the people, scuba diver people, easy to react with this oxygen, nitrogen gas that is completely dissolved in human blood. When divers come up, there is a release of dissolved gases and it leads to the formation of bubbles of nitrogen blood capillaries, which blacks. That's why these people, to avoid that, always along with these people always carry the cylinder, gas cylinder. These gas cylinders containing oxygen, which is diluted with air, helium and nitrogen, also oxygen, which is diluted with these certain ratios, that is nearly 11.7% of helium, 56.1% of nitrogen and 32.2% of this oxygen. Under these conditions, it cannot react and do not affect to the people. That's why at deep sea areas, its pressure is more than compared to the ground level. Okay, students. Then see one more applications of Henry's law. That is third one is, at a high altitude, the partial pressure of gas is less than that of ground level. This leads to low concentration of oxygen in the blood and tissues of people living at high altitude and climbers. See here, it is very important example. See the ground level, this is from a ground level to the upside. These are the climbers moving towards upward direction like Himalayas. Now at this position, here the oxygen, dissolved oxygen in blood is very less. That's why based on this, people at a high altitude cannot think properly. The disease is called anoxia. That's why based on this, maybe some questions will arise, some logical questions like at a higher altitude, cooking food in pressure cooker is difficult and will take more time because the pressure in ground level is more than compared to the high altitude pressure. So boiling point lowers, decreases. So that's why cooking time maybe increases. Means properly cannot cook food at a high altitude in a pressure cookers. Okay, students, this is very important. These three are very important applications of Henry's law. Okay, students. Okay, students. Yeah, based on Henry's law, there are some important objective questions for NEET, JEE and other competitive examinations. So here one theoretical question given here, students. Choose the correct statement about Henry's law. First one is, KH value is same for a gas in any solvent. It is not correct. It is wrong. Higher the value of KH, more the solubility of gas. No, this is also wrong. Higher the KH value, lesser the solubility. Higher the KH value, temperature also more. That's why it is not correct. Third one is here. KH value increase on increasing temperature. As on increasing temperature, KH value increases and its solubility decreases. Here students, solubility decreases. Now this is the correct one. Say the fourth one is, easily liquefiable gases usually has higher KH value. Now this is also a wrong. Lesser KH value is there for easily liquefiable gases. Okay, students. Say next one is here one question created like are the KH values of argon, it is considered as a 1, carbon dioxide, formaldehyde, methane are respectively given 40.3, 1.67, 1.83 into 10 power minus 3 and 0.413 at 298 kelvins. The increasing order of solubility of gas and liquid. Say it, students. On the basis of this, here KH is equals to P by X. This is the solubility. Now, increasing order of solubility we want. Increasing order we want. To get the more solubility, less KH values required. So, on the basis, in a given examples, here see here third one 1.83 10 power minus 5, that is 0.00183 value. It is very less. Less KH value is nothing but more solubility and the mole fraction is more. That's why among the given 4 options, once we can observe first and fourth one, 3 is there. 3 is their higher value, increasing order of their solubility. That's why remaining 2 and 3 options easy to eliminate. That is the best method to eliminate the unnecessary two important options. Remaining 2 only check it once. Now among these, next one is say here fourth one 0.413 value is less. Then compared to this, it is somewhat more, but here the solubility is more than compared to the carbon dioxide and argon. That's why fourth one is next higher solubility gas. That's why first option is the correct one for this. Okay, students. Theoretically, maybe based on this, they'll ask one question. Okay, next one is, say students, problems based on Henry's law. One is KH value for the solubility of nitrogen gas in water at 298 kelvins is 1 into 10 power 5 atmosphere. Okay. The mole fraction of nitrogen in air is 0.8. The number of moles of nitrogen from air dissolved in 10 moles of water at 298 kelvins and 1 atmosphere. Now students, underline this point. This is a very important. From air dissolved in 10 moles of water. Nothing but it is not the partial pressure of nitrogen. It is the total pressure given. Now, how many number of moles? This is the number of moles only given values, like 4 options created. This is also very important for objective as well as for theory. So here number of moles of nitrogen we want. Given that KH value given and mole fraction of N2 given 0.8 and number of moles of water also given, that is 10 moles, and total pressure created. Now students, we know our simple total pressure here. According to the Dalton's law of partial pressure, here Dalton's law of partial pressure, here the partial pressure of that particular nitrogen gas is equals to the product of total pressure and its mole fraction. On the basis 5 into 0.8, that is 4 atmospheric pressure obtained. Means out of this 5 moles of nitrogen atmospheric air, 4 moles of nitrogen is dissolved. Okay students, so finally we know partial pressure of nitrogen is equals to KH into mole fraction. We know already calculated now this partial vapor pressure of nitrogen 4 is equals to KH value given and its mole fraction. Mole fraction given already, that is in air, but here we want particularly in 10 moles of water only. That's why we can take separately as mole fraction of nitrogen is equals to 4 into 10 power minus 5. So calculated this value. By using this, we know its mole fraction of nitrogen is equals to ratio of any one component, means nitrogen number of moles by total number of moles. Compared to the water nitrogen number of moles, we can neglect here. Now number of moles of nitrogen by number of moles of water molecule. Now already this is mole fraction we know, then water molecule number of moles we know, water molecule number of moles we know, then cross multiply this, then we'll get the number of moles of nitrogen, that is 4 into 10 power minus 5 into 10, that is 4 into 10 power minus 4 number of moles it is. So for this answer is first one is the correct one, students. Okay students, see the next one is, the next problem is, if nitrogen gas is bubbled through water at 293 kelvins, how many millimoles, very very important students it is, millimoles of nitrogen gas would be dissolved in 1 liter water? Assume that nitrogen exerts a partial pressure of, given this partial pressure, given that KH for nitrogen at 293 kelvins is 76.48 K bar, like this. See here options also created just like above problem. Here given data is we want number of moles of nitrogen, partial pressure of nitrogen given, this is 0.987 bar, KH value given, but see here students, kilo bar given, this is, that is multiplied with 1000, then we'll get this, because this is bar and this is kilo bar, both are in same we want, that's what is multiplied with 1000 students. Okay, now we know partial pressure of that particular gas according to Henry's law, P is equals to KH into mole fraction of nitrogen. This value is there, partial pressure of nitrogen 0.987, and this value KH value is this, and mole fraction of nitrogen we want. So by using this relation we'll get a mole fraction of nitrogen is this, but we don't want a mole fraction, we want a number of moles of nitrogen. Compared to number of moles of water, number of moles of nitrogen is less, that's why we can neglect. So while doing some problems here, if it is very less and negligible, then we can neglect, we can take as number of moles of water only. We know this number of mole fraction of nitrogen 1.29 into 10 power minus 5 calculated here just like. Then substitute number of moles of nitrogen by total number of moles of water molecule. Here water molecule we can calculate because 1000 1 liter. Now 1000 by 1 liter is nothing but 1 kg, that is equals to 1000 grams only. 1000 by 18 its molecular mass, that's why 55.55 moles will get it. Then finally number of moles of nitrogen will get 7 into 7.16 into 10 power minus 4 moles. Okay students, now we want millimoles, 1 mole of that containing 7.16 into 10 power minus 4 moles of nitrogen, 1000 moles containing how much? If we can multiply, we'll get 0.716 millimoles. See here students, options. In second option, to confuse the children, given like this, 0.716 into 10 power 0, something power 0 is equals to 1. So answer is this. Okay students, next one is so here this is the in-text problem only from textbook. So here H2S gas is toxic with a rotten egg-like smell, is used for the qualitative analysis. If the solubility of H2S gas in water at STP is given, and calculate the Henry's law constant. Students, underline this point is very very important. 0.195 em, that indicates molality, nothing but the solubility of H2S in water at STP is means 0.195 moles of H2S is present in 1000 grams. So by using these water molecules number of moles we can identify easily. So at STP partial pressure of H2S is 1 atm, or we can use this. But depending upon the given values, means options in CET or NEET or any competitive examination, bar given, that's why better you take 0.987 bars. So we know that formula according to Henry's law, P is equals to KH into mole fraction. Now first calculate KH value. KH is equals to partial pressure by mole fraction. We know partial pressure of H2S and its mole fraction we can calculate. So here how to calculate mole fraction here given explained very clearly. Number of moles of H2S by total number of moles, because already total number of moles of H2S given. Don't neglect and don't take only number of moles of water molecule, students. Take both the number of moles, because already given in this given data. So by using this we'll get the mole fraction of H2S is this. So by taking this, K is equals to partial pressure of H2S by mole fraction of H2S, will get approximately 282. That's why it is the correct one. Okay students, next last problem. This is one simple problem. Last one is KH value for carbon dioxide in water is given 1.67 into 10 power 8 pascals at 298 kelvins. Calculate the quantity of carbon dioxide in 500 ml of soda water when packed under 2.5 atmosphere of carbon dioxide pressure at 298 kelvins. So based on this, given that 1.67 into 10 power 8 pascals and partial pressure of carbon dioxide is 2.5 atmosphere, both are not in same units, pascal and atmosphere. That's why anyone convert into same units. So here 1 atmosphere we know 101.325 pascal. Multiply with that, then we'll get in pascals. We know that partial pressure is equals to KH into mole fraction of carbon dioxide. First we want a mole fraction of carbon dioxide, that is simple formula is carbon dioxide by KH value in this law constant. This value we know, substitute here, we'll get a number of moles of mole fraction of carbon dioxide. By using this is to calculate the quantity of carbon dioxide, means number of moles or weight we want. For that, here the number of moles of water molecule given 500 ml, not 1000. In above problem given here 1000 grams means 1 liter. That's why here used 1000 grams. But here 500 ml given, better use 500 ml means 500 grams by 18. It's equivalent, its molecular mass. So water number of moles are 27.78 moles, students. So by using this, here mole fraction of carbon dioxide is equals to number of moles of carbon dioxide by water number of moles. So by using this value already calculated here, we know here. Then number of moles of carbon dioxide divided by 27.78, it is the number of moles of water molecule. Then number of moles of carbon dioxide will get like this, 42.14 into 10 power minus 3 or 0.0412 moles. This is the number of moles. If they ask number of moles, this is correct. Or if they ask weight, in terms of weight, we know number of moles is equals to weight by gram molecular weight. Already number of moles of carbon dioxide we know is equals to weight by gram molecular weight 44. Now weight is equals to cross multiply this